Welcome to this explainer. Okay, right off the bat, I want you to imagine we're stepping into a completely fascinating biological classroom. Picture your immune system as this incredibly eager, super capable student. And vaccines? Well, they're the meticulously crafted lesson plans designed to teach that student exactly how to protect you. Today, we're going to decode how these microscopic lesson plans are built, how our bodies actually learn from them, and why some of these lessons seem to stick literally forever, while others kind of need a refresher course.
So, let's dive into this universal curiosity. Look, we've all been to the doctor's office and experienced this, right? You get a tetanus shot, and the doc tells you you're good to go for a whole decade. But the flu shot? Yeah, you're back in that exact same chair every single year. And then meanwhile, you get a childhood measles shot, and you are essentially protected for the rest of your life. It's crazy. So what's with the massive discrepancy?
Well, to solve this mystery, we've mapped out a highly structured lesson plan of our own for this explainer. We're going to start with the lifelong immunity mystery, then look at how we build immunity, explore classic vaccine technologies, dive into the mRNA revolution, and finally, wrap up with exactly why some vaccines fade over time.
All right, kicking things off with Section 1, the lifelong immunity mystery, or the curious case of varied booster schedules.
Especially coming out of a post-pandemic world, vaccine fatigue is a very real thing for a lot of us. And the confusing reality of these widely varying shot schedules really doesn't make it any easier to understand. This brings us right to our core mystery. Look at the vast difference in durability here. 10 years for tetanus, 1 year for flu, lifelong for measles. It almost feels completely arbitrary, doesn't it? But I promise you it's absolutely not. It all comes down to a really complex dance between the specific type of invader and the exact tools our bodies use to fight them off.
Moving right along to Section 2, how we build immunity. Because before we can understand the medicine, we really need to meet the student itself, our incredible human immune system.
So there is a fundamental difference in how we actually acquire protection. First up, we've got passive immunity. This is immediate, sure, but it's totally temporary. It's basically borrowed protection. A super common example is what a newborn receives from their mom during the last couple of months of pregnancy, where maternal antibodies physically cross the placenta. But because those antibodies naturally degrade over a few weeks or months, that protection eventually fades. On the flip side, we have active immunity. Now, this is the holy grail. This is protection generated by your own immune system when it responds to a threat. That's what creates immunologic memory that can last for years or literally your entire lifetime.
When we hit that active immunity, we are essentially training the body's lifelong security force. And this force relies on two absolutely incredible cellular agents. First, we have memory B cells. Think of these as your elite intelligence officers. They remember the enemy's exact profile and rapidly deploy antibodies to block an infection before it even takes hold. But, sometimes just throwing antibodies at the problem isn't quite enough. That's when we look to our killer T cells. These guys are the cleanup crew. If antibodies fail and a cell actually gets infected, the killer T cells step right in to eliminate those infected cells entirely.
Okay, Section 3, classic vaccine technologies. Let's look at what we might call the traditional lesson plans.
So, how did we historically teach our immune student? Well, live attenuated vaccines use a weakened version of a germ. Since it's technically alive and can replicate just a tiny bit without actually causing the full disease, of course, it very closely imitates a natural infection. It's kind of like bringing in a real-life sparring partner for your immune system. This triggers a massive response from both those B cells and T cells, which is exactly why shots like the measles vaccine usually grant lifelong immunity. On the flip side, inactivated vaccines use a completely dead version of the germ. Think of this more like a practice dummy. It is incredibly safe for sure, but it mostly just produces antibodies with very little cellular immunity. So what happens? The memory fades, and you end up needing periodic booster doses just to remind the student what the threat looks like.
But wait, what happens when the bacteria itself isn't actually the direct problem, but rather some poison it secretes? Enter the toxoid. A toxoid is essentially an altered bacterial toxin. Think of it like a neutralized weapon. Scientists weaken the toxicity so it literally cannot harm you, but they maintain its immunogenicity. This forces your body's B cells to build specific, defensive immunoglobulins right against the toxin itself. And fun fact, this is exactly how we fight off nasty things like tetanus and diphtheria.
And modern medicine brilliantly combines these lessons. Take the classic DPT vaccine, for example. It doesn't just give your immune system one single lesson. It gives it 3 of them, all at once. It blends those neutralized weapons we just talked about, the toxoids of diphtheria and tetanus, right alongside the killed whole cells of the pertussis bacteria. It's just a beautifully efficient, multi-subject curriculum, all delivered in a single course to ensure you get optimal safety during adolescence and maturity. All right, let's jump to Section 4, the mRNA revolution, or as I like to call it, the modern blueprint.
Now, a lot of people seem to think mRNA technology just appeared out of thin air in 2020, but the foundation was actually laid way back in 1989 with the very first successful transfection of designed mRNA packaged inside a liposomal nanoparticle. Then fast forward to 2013, and we had the first human clinical trials for a rabies mRNA vaccine. So that incredible, mind-blowing speed we saw in 2020, resulting in the FDA emergency use authorizations for COVID-19, that wasn't a sudden miracle. It was the culmination of a carefully mapped-out, decades-long scientific journey.
So how does this modern blueprint actually work? It is just elegant biochemistry. Step 1, a tiny bubble of fat, a lipid nanoparticle, delivers a synthetic mRNA fragment right into your cell's cytoplasm. Step 2, your cell's own internal machinery, the ribosome, reads this mRNA just like an instruction manual. Then, Step 3 is where the real magic happens. Instead of a massive factory somewhere making the vaccine, your own cells produce the harmless viral antigen. And finally, Step 4, your immune system spots this foreign antigen and activates both B and T cells. Oh, and once the protein is built, the mRNA fragment, it's just naturally degraded by your body within a few days. No trace left behind.
This approach brings some staggering advantages to the table. First off is the sheer speed of design. Get this. Moderna was able to design their mRNA 1273 vaccine sequence in literally 2 days. 2 days! Second, because the antigen is produced inside the cell, it induces both cellular and humoral immunity, so activating both our rapid deployers and our cleanup crew. Third, and this is absolutely crucial, it has zero interaction with your genomic DNA. It never even enters the cell nucleus. And finally, because it's completely synthetically created, you aren't dealing with massive, risky vats of live infectious pathogens at production facilities.
Okay, bringing it to Section 5, why some vaccines fade, also known as the mutant factor.
So, if our technology is so amazing now, returning to our original mystery, why do some of these vaccines still fade? Well, we have to look at the pathogens themselves. The frustrating reality of the viral world is that not all viruses behave the same way. Stable viruses, like measles, polio, and smallpox, have very low mutation rates. They're super consistent, meaning the exact lesson our immune system learned decades ago still perfectly applies today. Boom, lifelong immunity. But then, we have fast mutating viruses. Think influenza and SARS-CoV-2. These guys replicate rapidly, constantly creating endless new variations of themselves. So your immune system might have a perfect, flawless memory of last year's flu, but this year's flu has completely changed its disguise. And that leads to temporary immunity and the dreaded need for regular boosters.
Hai Tran, the Associate Director of Pharmacy Services at Cedars-Sinai, explains this hurdle perfectly. He says, the more variants emerge, the harder it is to make a vaccine that will create lasting immunity because the target keeps moving. And honestly, that makes total sense. It is incredibly tough to teach a student when the textbook keeps changing every single semester.
But hey, the future is looking incredibly bright. Thanks to the mRNA revolution, we now have a tool that can actually keep up with this mutant factor. Pharmacist Ethan Smith notes that the sheer flexibility of mRNA is a total game changer. Scientists can just take the existing proven mRNA platform and literally swap out the genetic code to adapt to new mutations as fast as they appear. This means ensuring that your immunity stays continually primed over your entire lifetime.
Which leaves us with a really provocative thought to wrap up today's explainer. As we look ahead to 2026, which is actually slated to introduce single-shot combined mRNA vaccines for both influenza and COVID-19, it really begs the question, are we entering a bold new era where we can practically download instant software upgrades for our immune system's lifelong security force? The science definitely says yes, and the classroom is officially in the future. Thanks so much for joining me for this explainer. Keep asking those great questions, and I'll catch you in the next deep dive.